This is Lesson 5 on the unit on transition metal chemistry from Unit F325. In today's lesson we'll be looking at ligand substitution. The learning objectives for this lesson are to describe the process of ligand substitution and describe specific examples of ligand substitution using copper and cobalt complexes. For these reactions you'll need to know the colour changes, the shape and structures of the products formed. So let's start with the definition of ligand substitution, which is a reaction in which one ligand in a complex ion is replaced by another ligand. You need to describe the reactions that occur as water ligands are replaced by ammonia and chloride ions in the copper and cobalt hexa-aqua ions. Looking at the copper hexa-aqua ion first, this complex has the expected structure of an octahedron with a bond angle of 90 degrees and a typical pale blue colour. The cobalt complex ion is similar in structure, shape and bond angle but is a pale pink coloured solution. If you add excess concentrated hydrochloric acid to the copper complex, a ligand substitution reaction occurs and the 6 water ligands are swapped for 4 chloride ions. Concentrated hydrochloric acid is used to provide the chloride ions as it is a high concentration of them, but other solutions such as a saturated NaCl solution can also be used. The reaction that occurs is a reversible reaction and the equilibrium that is set up is shown on the slide. As chloride ions are bigger than water molecules, only 4 can fit around the central copper ion, so the coordination number is reduced to 4 and the shape is now tetrahedral with a bond angle of 109.5. In terms of the colour change you need to know, the blue hexa-aqua ion turns to a yellow tetrachlorocuprate ion. However, in practice, this is often seen to be green as it is a mix of the initial blue and yellow colours. If you add enough chloride ions, it will go yellow, and this is the colour that you need to learn. These ligand substitution reactions are all equilibrium reactions, and this reaction can go in reverse direction with the yellow turning to blue if water is then added to excess. This follows Le Chatelier's principle. If you add excess concentrated hydrochloric acid to the cobalt hexa-aqua ion complex, a similar ligand substitution reaction occurs, whereby the 6 water ligands are swapped for 4 chloride ions. This is a simple colour change, with the pink solution turning to a dark blue solution. Again, it is a reversible reaction and the colour can go back from blue to pink if water is then added to excess. The situation is a little more complex for ligand substitution with ammonia. This is because ammonia can also act as a base. If you remember back to the topic on acids and bases, a base is a proton acceptor. An ammonia molecule, NH3, can accept a proton to form an ammonium ion, NH4+. The reaction on the slide shows that the copper hexa-aqua complex reacts with 2 ammonia molecules to form the insoluble neutral complex, which is the blue precipitate that forms in the precipitation reaction between copper 2+ solution and an aqueous sodium hydroxide. When we covered precipitation reactions, we simplified the formula of the precipitate to CuOH2. So the first observation when we add dilute ammonia solution to copper hexa-aqua complex is that the blue solution forms a pale blue precipitate. When excess ammonia or concentrated ammonia is added, the precipitate dissolves and a ligand substitution reaction occurs where 4 of the water ligands are replaced by ammonia molecules. Ammonia and water molecules are of a similar size, so the complex remains with a coordination number of 6 and an octahedral shape. It's important to note that all 4 ammonia molecules are in the same plane and the complex has trans-isomerism. This solution, with a copper complex ion with 4 ammonia ligands and 2 water ligands, is a deep blue colour. So to summarise the stepwise reactions of the hexa-aqua copper complex with ammonia, the solution is initially blue, and the species responsible is CuH2O6 with an overall charge of +2. On addition of a small amount of dilute ammonia, a pale blue precipitate forms, and the species responsible is CuOH2, copper hydroxide. When ammonia is added to excess, the solution turns a dark blue colour and the species responsible is CuNH34H2O2, and this has an overall charge of +2. Let's now switch our attention to the ligand substitution reactions of the cobalt hexaqua ion, which is pink in colour. In a similar reaction to the copper equivalent, when we add a small amount of dilute ammonia, a green precipitate of cobalt hydroxide is formed. Adding ammonia to excess, this time replaces all of the water ligands with ammonia ligands to form a straw-coloured solution. The overall ligand exchange reaction is shown on the slide, again with the reversible arrow to show it is in equilibrium. So let's revisit the learning objectives for this lesson. You should now be able to describe the process of ligand substitution, exemplified by that of copper and cobalt. Although these are the only ones you need to be able to state the colour changes for, you should be prepared to recognise ligand substitution reactions for unfamiliar transition metals and unfamiliar ligands, and suggest equations and structures for the products. During class time, you will carry out a practical involving different ligand substitution reactions so you can observe the colour changes for yourself. We'll see you then.